Something appeared in the Martian sky on October 4, 2025 that changed everything we thought we knew about our place in the universe. The Perseverance rover, sitting alone in Jezero crater, captured an image that would ignite the internet and divide the scientific community into two warring camps. This wasn't a smudge on the lens. This wasn't a fleeting dot of light. This was an elongated, glowing object stretching across the darkness, for times longer than it was wide, radiating an eerie luminescence that shouldn't exist at that distance from the sun. Within hours, the world split into believers and skeptics. Harvard astrophysicist Avi Loeb attempted to explain it away as a simple camera illusion, stacked images creating false elongation. But Dr. Horace Drew, a scientist with credentials from Caltech and Cambridge, fired back with mathematics that refused to cooperate with comfortable explanations. If a green nickel cloud surrounded this thing, he argued, the center should glow green too. Instead, it blazed white, brilliant and defiant against every natural law we understand. But the real mystery wasn't what we could see. It was what they wouldn't show us. NASA went dark. Then the European Space Agency. Then China, who never misses an opportunity to showcase their Mars achievements for propaganda. Then the United Arab Emirates. For rival space agencies, competitors on the world stage, suddenly unified in their refusal to release images from the closest flyby in recorded history. The timing sent chills through anyone paying attention. NASA's government shutdown began October 1st, exactly 48 hours before the flyby. Coincidence? Perhaps. But as 3I/Atlas raced toward the sun, approaching its perihelion on October 29th, two terrifying possibilities emerged. Either we're witnessing the most chemically bizarre comet ever discovered, pumping out industrial-grade nickel alloys and violating every natural explanation in our textbooks, or something infinitely more extraordinary is happening in the darkness above Mars. Something they don't want us to know about. I'm going to walk you through every piece of evidence they tried to bury. The photographs that defy physics. The silence that screams conspiracy. The chemical signatures that match spacecraft alloys better than they match any natural object. The mathematical impossibilities in its trajectory. And most disturbing of all, what might have happened on October 29th when this object reached perihelion, hidden behind the sun where Earth's telescopes couldn't watch. Before we dive deeper, I need you to do three things. First, hit that subscribe button right now. This channel brings you the stories mainstream science doesn't want publicized, and algorithms suppress content like this unless you actively support it. Second, understand that what you're about to hear isn't speculation. It's documented evidence from peer-reviewed papers, official observations, and leaked data that powerful institutions wish had stayed buried. And third, smash that like button because engagement tells me you want more investigations like this. If you make it to the end of this video, and I promise the conclusion will shake you, leave a comment telling me what you think happened on October 29th. Was it a comet, or was it contact? Your answer matters, and I read every single comment. Now let's go back to the beginning, to the moment when everything changed. October 4th, 2025 will be remembered as either humanity's awakening or our greatest failure of perception. The Perseverance rover had been given unusual instructions in the days leading up to this moment. Engineers on Earth, working with what they thought was a routine astronomical opportunity, prepared the rover for an observation session unlike any it had conducted before. The object designated 3I/Atlas, the third confirmed interstellar visitor ever detected by human instruments, was making its closest approach to Mars. 38 million kilometers separated them, a distance that sounds vast but represents an astronomical handshake, the best chance humanity would ever get to examine something that originated beyond our solar system's protective bubble, something born in the darkness between stars where no human probe has traveled and no telescope can reach. The rover's navigation camera began its imaging sequence. These weren't the sophisticated color cameras that produced those breathtaking panoramas of rust-colored Martian landscapes we've all seen. The NAVCOM serves utilitarian purposes, helping the rover navigate terrain, avoid obstacles, plan routes across hostile ground. It captures in black and white with an angular resolution of 33 milliradians per pixel, technical specifications that mean nothing until you translate them to actual scale. At 38 million kilometers, each pixel represents roughly 12,500 kilometers of space. Think about that measurement. Each single pixel covers an area larger than Earth's entire diameter. You're not going to see fine details. You're not going to distinguish surface features or read markings. But you should absolutely be able to detect the general shape of something, especially when multiple images are combined using standard astrophotography techniques to reduce noise and amplify genuine signals. And that's precisely what happened next. The Perseverance operations team, or more accurately, the amateur astrophotographers who monitor raw image feeds with obsessive dedication, began stacking the NAVCOM frames. Not just a handful of images, but hundreds of them, captured over approximately 10 minutes of Martian time. This stacking process represents common practice in astrophotography worldwide. When you're attempting to photograph something faint, something barely visible against the cosmic background, you combine multiple exposures. Random noise, the static that plagues every digital image, averages out and disappears. Real signals, genuine features actually present in the frame, accumulate and strengthen. This is how amateur astronomers using backyard telescopes capture stunning images of nebulae billions of kilometers away. This is how professionals tease out the faintest galaxies at the observable universe's edge, galaxies so distant their light has traveled for over 13 billion years to reach our instruments. When those hundreds of frames were stacked and processed, something materialized that shouldn't exist. Not a circular dot like every asteroid we photographed. Not a fuzzy blob with the characteristic tail streaming behind it like every comet observed from Earth throughout human history. What appeared was a stripe, an elongated feature approximately 4 times longer than its width, glowing against the background stars with an intensity that suggested substantial mass and reflectivity. Most critically, it appeared white in the center with distinct hints of green radiating around the edges, a color distribution that would become one of the investigation's most controversial elements. The image exploded across social media within hours of its release. Reddit threads accumulated hundreds of comments before moderators could even organize the discussions. The platform formerly known as Twitter became a battleground where amateur astronomers, conspiracy theorists, professional scientists, and everyone between offered interpretations ranging from measured analysis to wild speculation. YouTube channels rushed content into production, enhancing contrast, drawing conclusions, generating millions of views on videos uploaded within 24 hours of the original image's appearance. At the center of this digital firestorm sat a question that seemed deceptively simple but carried implications that extended far beyond astronomy. What are we actually looking at? The mainstream explanation arrived with reassuring speed. Avi Loeb, professor of astrophysics at Harvard University and director of the Galileo Project, had been monitoring 3I/Atlas since its discovery back in July. He'd already published preliminary papers suggesting the object displayed unusual properties, chemical and physical anomalies that didn't quite align with standard cometary profiles. But when the Perseverance image went viral with thousands of people asking whether it showed a cylindrical spacecraft, Loeb took to his widely read blog to explain what he believed was occurring. The elongation, he carefully wrote, represented an artifact not of alien engineering but of straightforward physics governing how cameras work when objects are in motion. 3I/Atlas was traveling at approximately 67 kilometers per second relative to the Sun, following a retrograde orbit moving opposite to the direction planets travel around our star. From Mars's perspective, accounting for the planet's own orbital motion, the object was screaming across the sky at tremendous velocity. Over 10 minutes, the duration of the imaging sequence, it would travel roughly 50,000 kilometers through space. If you're stacking hundreds of individual frames taken throughout that time period, Loeb explained, you're essentially creating a time-lapse photograph. The object's motion gets smeared across the final composite image, producing the visual illusion of elongation. It's identical to photographing a car driving past at night using a long exposure setting. The car itself might be compact, conventionally shaped, but in the photograph it appears as a streak of light stretched across the frame, headlights and taillights leaving luminous trails behind them. You wouldn't conclude the car was shaped like a ribbon simply because the photograph displayed it that way. Loeb calculated the numbers with characteristic precision. The NAVCOM's angular resolution meant each pixel encompassed 12,500 kilometers at 3I/Atlas's distance during closest approach. The stripe appeared approximately 50,000 kilometers in length. Divide that distance by the object's velocity relative to Mars, roughly 91 kilometers per second when accounting for both objects' motions through space, and you derive approximately 9 to 10 minutes. That number matched perfectly with the integration time required to stack enough frames to bring a faint object above the noise threshold, to make it visible against the background static. The mathematics checked out flawlessly. The explanation felt elegant, straightforward, grounded in well-understood principles of imaging and kinematics that undergraduate physics students learn. Case closed, problem solved, mystery explained, right? Not according to everyone watching. Dr. Horace Drew, who operates online under the handle Red Kali, isn't someone easily dismissed or ignored. His credentials include significant work at Caltech and the MRC Laboratory of Molecular Biology in Cambridge. He's published peer-reviewed research on DNA, contributed to investigations of crop circles, and described what he interprets as extraterrestrial mathematical codes embedded in various phenomena. To supporters, he represents a maverick willing to explore ideas the mainstream reflexively rejects. To critics, he's ventured too far into speculation, abandoned scientific rigor for sensationalism. But his counterargument to Loeb's motion blur explanation raised eyebrows throughout the community because it focused on something directly observable in the images themselves, something that couldn't be dismissed as interpretation or bias. Drew pointed out with careful emphasis that enhanced color versions of the stacked images revealed something crucial to the entire debate. The stripe center appeared distinctly white while the edges showed a pronounced greenish tinge. This coloration, he argued forcefully, aligned perfectly with observations of 3I/Atlas from Earth-based telescopes showing a green nickel-rich coma, a cloud of ionized gas surrounding the nucleus. If the elongation resulted purely from stacking images of a small rocky nucleus moving through a larger green coma over time, then combining those frames should result in the central stripe appearing predominantly green. There would be so much accumulated green color from the coma in each individual frame that the final stacked image couldn't possibly maintain a bright white center. The green would overwhelm everything, dominating the color balance. Unless, Drew suggested with implications that sent ripples through online discussions, the object itself possesses an extended white shape, an actual elongated structure significantly larger than the green coma surrounding it. In that scenario, stacking the images would naturally preserve white dominance in the center because there's simply more white-emitting material than green in each frame. It becomes a geometric argument about ratios, about how colors combine when you integrate hundreds of slightly different images. And crucially, it's not easily dismissed without detailed modeling of what the coma's extent and brightness would be at that distance, how it would appear in NAVCOM's black and white captures that were later colorized using standard astronomical techniques, and what the actual nucleus size, shape, and composition might be. Drew also emphasized with growing urgency that multiple Mars orbiters from different nations had photographed 3I/Atlas during the flyby. The Mars Reconnaissance Orbiter with its powerful high-rise camera. Mars Express carrying sophisticated spectrometers. ExoMars Trace Gas Orbiter equipped with the Cassis Color Imaging System. China's Tianwen-1, their first successful Mars mission. The UAE's Hope probe, the Arab world's triumphant entry into interplanetary exploration. Every single one of these spacecraft had pointed instruments at 3I/Atlas during its closest approach on October 3rd. Multiple nations, rival space programs, competing for prestige and scientific priority, all positioned to capture the best images ever taken of an interstellar object. And yet, as October 6th arrived and Drew and dozens of other analysts were posting their competing interpretations, not a single official processed image had been released by any space agency anywhere on Earth. The raw Perseverance NAVCOM frames were publicly available because NASA posts them automatically through systems designed to operate without human intervention. But the high-resolution images from HiRISE, capable of 30 km per pixel resolution at 3I/Atlas's distance during closest approach, remained mysteriously unreleased. The spectroscopic data that could definitively reveal the chemical composition of the coma stayed locked behind institutional walls. The color images from Cassis on ExoMars, the infrared observations from Hope Samir's instrument, all of it remained in official databases, unseen by the public that funded these missions. Why the deafening silence? NASA's answer came wrapped in bureaucratic language. The United States government had entered a funding shutdown on October 1st, 2 days before the critical flyby. Thousands of NASA employees were furloughed, sent home without pay. Websites weren't being updated. Press releases weren't being drafted or approved. The agency, in its own carefully worded statements, was operating with skeleton staff focused exclusively on mission-critical activities. Processing and releasing images of an interstellar comet, regardless of scientific interest, apparently didn't qualify as mission-critical during a budget crisis. But the timing struck many observers as suspicious beyond credibility. A shutdown beginning precisely 48 hours before the most anticipated astronomical observation in years felt almost too convenient to accept as coincidence. And crucially, it didn't explain why the European Space Agency, operating completely independently of American budget politics and congressional dysfunction, also remained absolutely silent. It didn't explain why China, which routinely releases images from Tianwen-1 as a matter of national pride and to showcase their space program's rapidly advancing capabilities, had shared nothing. It didn't explain why the United Arab Emirates, desperately eager to demonstrate the success of their Hope Mars mission, their nation's first interplanetary probe and a source of enormous pride, hadn't jumped at the opportunity to show the world what their instruments captured. This wasn't one sluggish agency dragging its feet on data release. This was coordinated silence across geopolitical rivals, nations that actively compete for prestige, funding, and influence in space exploration. Nations that don't cooperate, that don't share data, that view each other's space programs with mixture of admiration and suspicion. And that silence, that unprecedented unified refusal to release routine scientific data, became a story larger than any single photograph. Because in the absence of official information, speculation doesn't just fill the void, it floods it completely, overwhelming rational analysis with theories ranging from plausible to absurd. If you're still watching, you're part of a community that refuses to accept comfortable lies instead of uncomfortable truths. Show your support by hitting that like button right now. This video represents dozens of hours researching scientific papers, analyzing data, and connecting dots that powerful institutions hope you never connect. The algorithm suppresses this kind of content unless engagement proves people want it. And believe me, what's coming next will challenge everything you think you know about our solar system's security. Stay with me. The debate crystallized into what resembled a scientific duel, except instead of playing out in peer-reviewed journals with their months-long review processes and careful editorial oversight, it exploded in real time across blogs, social media platforms, and hastily organized video conferences. This wasn't how astronomy typically operates. Usually, observations are methodically made, Data is carefully analyzed over weeks or months. Papers are written with painstaking attention to detail, submitted to journals, revised based on peer feedback, and eventually published. The process takes time, demands patience, requires rigor. Peer review ensures errors get caught, alternative explanations get properly considered, conclusions get supported by sufficient evidence rather than speculation. But 3I/Atlas didn't allow that luxury of time. It was moving, traveling millions of kilometers closer to the sun with each passing day, approaching perihelion on October 29th when it would swing around our star at its closest point. After that critical date, it would begin its journey back outward, accelerating as it climbed away from the sun's gravitational well, eventually leaving our celestial neighborhood forever. The window to observe it, to gather comprehensive data, to understand what it truly represented, that window was closing with terrifying speed. And so the scientific debate happened in fast forward, with credentialed scientists, experienced amateur astronomers, and millions of interested observers all weighing in simultaneously through whatever platforms they could access. The core question seemed deceptively simple on its surface. Was the elongated appearance in the Perseverance images a genuine physical characteristic of 3I/Atlas? Or was it an optical illusion created by the specific way the images were captured and subsequently processed? Understanding why this matters requires grasping what each possible answer implies about reality itself. If it's a camera artifact, then 3I/Atlas is likely a relatively compact object, perhaps a few kilometers across, surrounded by a diffuse coma of sublimating gas and reflective dust particles. Unusual, certainly, given its interstellar origin and the bizarre chemical composition already documented. But fundamentally still a comet, strange chemistry notwithstanding, odd trajectory acknowledged, but ultimately a natural object formed in another star system billions of years ago, ejected by gravitational interactions with forming planets, wandering through interstellar space, and now passing through our solar system entirely by chance. If it's not an artifact, if the object genuinely possesses an elongated structure stretching 4 times longer than its width, then the entire conversation shifts dramatically into uncomfortable territory. Natural objects in space tend toward certain predictable shapes dictated by physics. Small bodies remain irregular like asteroids because their gravity isn't strong enough to pull them into spheres. Larger bodies become spherical or oblate spheroids if they're rotating rapidly, flattened at the poles by centrifugal force. Elongation ratios of 4:1 are exceptionally rare for natural objects. Not impossible, physics doesn't forbid them, but requiring very specific formation scenarios or structural compositions that can support such shapes against gravitational collapse or tidal forces that would normally tear elongated objects apart. An elongated structure immediately invites comparison to Oumuamua, the first confirmed interstellar object discovered in October 2017. Oumuamua was also elongated, with astronomers estimating a ratio of roughly 10:1 based on how its brightness varied as it tumbled through space, reflecting different amounts of sunlight depending on which face pointed toward Earth. That extreme elongation sparked endless debate that continues to this day. Some researchers argued it represented a cigar-shaped asteroid, perhaps a fragment from a planetary collision in another star system. Others suggested it might be a flat disk seen edge-on, like viewing a pancake from the side, which would also produce the observed brightness variations during rotation. And Avi Loeb himself had proposed, controversially enough to generate both international headlines and professional criticism, that Oumuamua could represent a light sail, an extremely thin artificial structure designed to be pushed by stellar radiation pressure, a technology concept humans have explored for potential interstellar travel. Oumuamua's elongation combined with its non-gravitational acceleration as it departed the solar system, acceleration that couldn't be fully explained by standard cometary outgassing models, made it profoundly anomalous. The scientific community largely settled on exotic but still natural explanations. perhaps hydrogen ice sublimating in ways that wouldn't produce visible tails. Perhaps solid nitrogen icebergs similar to what might exist on Pluto's surface. But the debate never fully resolved, and Loeb has continued arguing that artificial origins shouldn't be reflexively dismissed without definitive evidence. Now humanity faced 3I/Atlas, potentially showing elongation again in high-quality images. If real, if confirmed by additional observations, it would represent the second highly elongated interstellar object out of only 3 ever detected by our instruments. That's not just coincidence, that's a pattern. 2 out of 3 equals 67%. If elongated shapes are exceptionally rare among natural solar system objects but common among interstellar visitors, you're forced to ask deeply uncomfortable questions. Why are interstellar objects different? What makes them elongated when natural selection through collisions and gravitational interactions should favor more compact shapes? Are we observing selection effects where only certain shapes survive ejection from their home systems and the brutal journey through interstellar space? Or are we witnessing something else entirely, something our current frameworks can't accommodate? The mathematical arguments became increasingly intricate as more researchers entered the fray. Several astrophysicists not directly involved in the Loeb versus Drew exchange started running their own independent simulations. If you model 3I/Atlas as a point source, essentially treating it as you would a distant star, then track how that point would appear to move across Martian sky over 10 minutes of observation, you can generate synthetic images. Blur each position slightly to account for the NavCom's resolution limits. Stack them using identical algorithms to what amateur processors used. See what emerges from the simulation. Those computer-generated tests generally supported the artifact explanation. A moving point source, when tracked across the sky and stacked into a composite image, produces an elongated streak. The streak's length matches the distance traveled during the total exposure time. Its basic kinematics combined with image processing, nothing exotic or mysterious. But those simulations rested on critical assumptions that might not reflect reality. They assumed 3I/Atlas was effectively point-like, that its brightness was concentrated in a very small nucleus rather than spread across an extended region. What if the coma was already extensive at that distance, already dozens or hundreds of kilometers across, glowing from fluorescence as sunlight ionized its gas? Then each individual frame wouldn't capture a point of light but rather a fuzzy disk. Stacking fuzzy disks over time while they move creates a fundamentally different result than stacking point sources. The streak becomes more smeared, less sharply defined. The brightness distribution changes in measurable ways. And here's where observations diverged from simple simulations in troubling fashion. The images showed relatively sharp edges on the elongated feature. Not perfectly sharp, atmospheric blur and instrument limitations prevent that, but sharper than you'd expect if you were stacking images of a large diffuse coma moving across the frame over 10 minutes. That sharpness suggested either the coma was smaller than theoretical models predicted, or the nucleus was exceptionally bright relative to the surrounding coma, or something about the object structure was indeed genuinely elongated rather than created by motion blur. Then the color analysis added another layer of complexity that refused simple resolution. Drew's observation about the white center versus green edges wasn't something professional astronomers could easily wave away. Other experienced amateur astronomers started pulling up their own ground-based observations from early September when 3I/Atlas had been photographed during a total lunar eclipse. Those images, taken with tracking telescopes that compensated for the object's motion by following it across the sky, showed 3I/Atlas with what appeared to be an extended white core surrounded by a greenish halo, visible even from Earth's tremendous distance. One astrophotographer named Gerald Riemann, who had imaged dozens of comets over his decades of experience, noted that the structure seemed highly atypical compared to every comet he'd previously captured. Most comets show a bright central nucleus with a gradually fading coma, more or less circular or slightly elongated in the direction away from the Sun due to radiation pressure pushing dust and gas outward. 3I/Atlas in his carefully processed images looked fundamentally different. The white region appeared elongated even when properly tracked to eliminate motion blur, and the green coma seemed to form a distinct separate layer around it, rather than a uniform glow fading smoothly from center to edge. If you took those ground-based observations seriously, and these were experienced observers using quality equipment, they suggested the white elongated appearance wasn't purely a Perseverance imaging artifact. It was already visible from Earth's distance, though harder to see clearly due to atmospheric distortion and the much greater distance reducing apparent size. Professional astronomers began offering measured commentary with characteristic caution. Several pointed out through journal articles and blog posts that determining the true shape of any comet from Earth, or even from Mars' orbit, remains fraught with technical challenges. You're never seeing the solid nucleus directly. You're seeing sunlight scattered by dust particles and fluorescent emission from ionized gas surrounding the nucleus. The distribution of that dust and gas depends on how the nucleus is outgassing, which depends on its rotation rate, its surface composition, the angle of incoming sunlight, temperature gradients, and a dozen other variables. A perfectly spherical nucleus with uneven outgassing from localized active regions can create asymmetric comas that appear elongated from certain viewing angles. Historical observations have documented this effect in multiple comets. But other researchers noted that 3I/Atlas had already proven itself profoundly unusual in multiple independent ways beyond just the shape debate. The chemical composition kept emerging as a central mystery that no simple explanation could resolve. Space-based observations from the James Webb Space Telescope conducted in early August had revealed something unexpected that contradicted everything we know about typical cometary chemistry. Most comets throughout our solar system are rich in water ice. When they approach the Sun and surface temperatures rise, water sublimates off, transforming directly from solid ice to vapor without passing through liquid phase. This sublimating water creates the characteristic tails we associate with comets, spectacular displays visible even to ancient humans who interpreted them as omens. But 3I/Atlas was chemically different in ways that defied comfortable explanation. Webb's spectrograph revealed that the coma was overwhelmingly dominated by carbon dioxide, not water. 87% carbon dioxide by mass, 9% carbon monoxide, and only about 4% water. Let that ratio sink in for a moment. 8:1 carbon dioxide to water. That's not just unusual, it's extreme beyond anything documented in solar system comets. Our comets typically show the opposite ratio, vastly more water than carbon dioxide, because they formed in a solar system where water ice was abundant. Some comets originating from the Oort cloud, the distant spherical shell of icy bodies surrounding our solar system far beyond Pluto's orbit, show somewhat elevated carbon dioxide relative to inner solar system comets, but nothing remotely approaching this level. The only other interstellar comet previously observed, 2I/Borisov discovered in 2019, had shown water-dominated chemistry remarkably similar to our own solar system's comets, suggesting common formation processes despite different stellar origins. Why was 3I/Atlas so utterly dry, so depleted in the most common volatile in the universe? One explanation involved formation temperature. If it formed in an exceptionally cold region of its home star system, significantly farther from its parent star than Earth orbits our Sun, then water ice might have been depleted early in its history while carbon dioxide remained abundant. Or if 3I/Atlas had been wandering through interstellar space for billions of years, cosmic rays and ultraviolet radiation from passing stars could have gradually altered its surface composition, preferentially destroying water molecules while carbon dioxide remained more stable. But another chemical oddity compounded the mystery in ways that pushed natural explanations to their breaking point. observations from the Very Large Telescope in Chile had detected nickel atoms in the coma at concentrations that made no sense. Nickel itself isn't shocking in cometary spectra. Many comets show trace metals released when dust grains get heated. But 3I/Atlas was producing nickel at extraordinary rates that increased dramatically as it approached the Sun. And most troubling of all, it was producing abundant nickel without corresponding iron detection. In every natural environment we've ever studied, nickel and iron are inseparable companions. They form together in the cores of dying stars during supernova nucleosynthesis. They get blasted into space together when those stars explode. They condense into planets, asteroids, and comets together because they're chemically similar. Every meteorite ever analyzed, every asteroid sample returned to Earth, every piece of cosmic material studied in laboratories shows nickel and iron in relatively consistent ratios. They're geochemical twins that nature doesn't separate under normal conditions. Separating them requires industrial processes, deliberate refining, technological intervention. On Earth, we refine nickel away from iron when we need pure nickel for specialized applications. Nickel plating for corrosion resistance. Nickel-based superalloys used in jet engines that must withstand extreme temperatures. Spacecraft components requiring materials that won't degrade under radiation bombardment. These technologies require separating nickel from iron through chemical or electrochemical processes that don't occur in nature. The Very Large Telescope data showed nickel emission increasing dramatically as 3I/Atlas approached the Sun. In just 1 month spanning July to August, the production rate increased 25-fold. That's not a gradual rise, that's an explosion of nickel release. That steep increase following a power-law relationship with solar distance suggested something about the object's surface was being preferentially heated and releasing nickel, while somehow iron remained locked in stable compounds that weren't vaporizing. Natural explanations existed, but they required invoking exotic chemistry never before observed. Perhaps nickel carbonyl compounds, molecules rarely seen even in laboratory settings, were sublimating off the surface while iron compounds remained stable at the same temperatures. It would be unprecedented but not physically impossible. Or perhaps the surface had a layered composition with nickel-rich minerals coating the exterior and iron-rich materials beneath, and only the surface layer was reaching temperatures sufficient to release metals. Yet the alternative explanation, the one that generated headlines and raised eyebrows throughout the scientific community, was that the nickel signature matched perfectly what you'd expect from technological materials. If 3I/Atlas was artificial rather than natural, if it possessed a metallic hull or structural framework, nickel alloys would make perfect engineering sense. They're exceptionally durable, highly resistant to radiation damage, stable across enormous temperature ranges from nearly absolute zero to hundreds of degrees. Exactly what you'd want for a probe designed to survive traveling between stars for millions or billions of years. Make it to the end, and I'll reveal what the data suggests really happened on October 29th when 3I/Atlas passed perihelion hidden from Earth's view. It's not what NASA is telling you. But first, if this investigation is opening your eyes to realities they'd prefer stay hidden, hit that subscribe button and turn on notifications. Content like this gets suppressed, and I can only continue producing it if you actively support the work. Drop a like right now to tell the algorithm that truth matters more than comfortable ignorance. The chemical impossibilities kept accumulating like evidence in a trial where the verdict grows increasingly clear despite attempts to muddy the facts. But suggesting any object might be artificial based solely on chemical composition represents a tremendous leap, one requiring extraordinary evidence that remains frustratingly absent. It demands proof beyond mere anomalies, beyond statistical unlikelihood, beyond even multiple compounding mysteries. Still, all the observations could theoretically be explained, however awkwardly and unconvincingly, through natural processes. Strange natural processes, granted, processes humanity has never witnessed before in our limited sampling of the cosmos. But that's precisely what makes interstellar objects so scientifically valuable. They're physical samples from other planetary systems, places we cannot visit with current technology, stellar environments where conditions might have been dramatically different from our own solar system's formation 4.6 billion years ago. The debate over whether the elongation was genuine structure or imaging artifact refused to resolve because both interpretations had valid points that couldn't be easily dismissed through rhetoric or authority. And underneath the technical arguments lay a growing realization spreading through online communities and whispered in university astronomy departments. The photographs were only one piece of a larger puzzle. The chemistry provided another piece. But what mattered equally, perhaps even more significantly, was what we weren't being shown. The data that should have been routinely released but remained locked away. The observations that multiple space agencies had undoubtedly made but refused to share with the public that funded their missions. The silence that seemed to grow louder, more deliberately coordinated, with each passing day. Consider China's historical track record with Tianwen-1 data releases. The China National Space Administration has published over 14,000 images from the Tianwen-1 Mars orbiter since it entered Martian orbit in February 2021. These aren't just raw data dumps posted to satisfy technical requirements. They're carefully processed, beautifully rendered images released with accompanying press statements in English and Mandarin, often timed precisely to coincide with national celebrations or to underscore China's rapidly growing capabilities in space exploration. When Tianwen-1 captured a stunning global color map of Mars at 76 meters per pixel resolution, those images appeared on government websites within days. When the accompanying Zhurong rover successfully landed on the Martian surface and began transmitting photographs, China ensured the entire world saw them immediately, translating materials into multiple languages for international consumption. This behavior isn't unusual or unexpected. Space agencies worldwide use their successes to justify enormous budgets, to inspire the next generation of scientists and engineers, to demonstrate technological prowess to rival nations. During the Cold War, the space race between the United States and Soviet Union functioned as much as propaganda competition as it did scientific exploration. Every satellite launch, every human spaceflight, every lunar landing represented a carefully orchestrated statement to the world. We possess this capability. We have achieved this milestone. We are technologically advanced and powerful. That fundamental competition never truly ended. It simply evolved into new forms. Today, China and the United States view each other as primary rivals in space, a competition with implications for military capabilities, economic advantages, and global prestige. The Artemis Accords, an American-led framework for lunar exploration and resource utilization, deliberately excludes China from participation. In response, China has partnered with Russia to plan an international lunar research station, an explicit counter to American dominance. The two space powers barely coordinate on anything. The Wolf Amendment, passed by the United States Congress in 2011, explicitly prohibits NASA from bilateral cooperation with China without special congressional approval. They don't share data. They don't collaborate on missions. They actively compete for achievements and firsts. So when 3I/Atlas made its closest approach to Mars and both NASA's Mars Reconnaissance Orbiter and China's Tianwen-1 had perfect vantage points to observe this historic flyby, you would absolutely expect each agency to rush their results to publication, competing to be first with analysis and images. Imagine the headlines that would typically follow. China captures unprecedented images of interstellar visitor. NASA's HiRISE provides clearest view yet of mysterious comet. These represent exactly the kind of scientific achievements that play exceptionally well both domestically and internationally, the kind that justify continued funding and generate genuine public excitement about space programs. But neither agency released anything at all. Not processed images showing what their sophisticated instruments captured. Not preliminary scientific analysis offering even basic findings. Not even brief official statements confirming successful observations occurred. NASA pointed to the government shutdown, which was undeniably real and did furlough thousands of civilian employees. But the shutdown didn't prevent Perseverance rover from continuing to post raw NavCam images automatically through systems designed to run without continuous human oversight. Those images upload through data management protocols that function autonomously. If raw NavCam images could still reach public servers during the shutdown, why couldn't raw high-rise images follow the same automated pathway? Why couldn't China, operating completely independently of American budget politics and congressional dysfunction, release anything from Tianwen-1's observations? The United Arab Emirates added yet another troubling layer to this mystery. Their Hope orbiter, officially called the Emirates Mars mission, was explicitly designed to study the Martian atmosphere across daily and seasonal cycles using a comprehensive suite of instruments. It carries the Emirates Mars infrared spectrometer and the Emirates Mars ultraviolet spectrometer, perfect tools for analyzing the chemical composition of a comet's coma, for detecting trace gases, for measuring how different molecules interact with solar radiation. And Hope maintained a clear, unobstructed line of sight to 3I/Atlas during the October 3rd flyby when the object passed nearest to Mars. The UAE has been extraordinarily, justifiably proud of Hope since before launch. It represents the Arab world's first interplanetary mission, a stunning achievement for a nation that established its space agency only in 2014. The mission team regularly publishes data through their online portal, releases detailed updates, actively engages with both scientific communities and general public. The UAE Space Agency maintains robust social media presence across platforms, celebrating achievements, sharing science results, engaging with educational outreach. Their transparency has been exemplary, setting standards other nations' space programs should emulate. Yet after October 3rd, absolutely nothing emerged from their data archives. No images showing 3I/Atlas as captured by Hope's instruments. No spectroscopic data revealing what molecules were detected in its coma. No official mention of observations beyond a brief pre-flyby statement in late September confirming they would be observing this rare opportunity. It was as if the entire event simply never occurred from their institutional perspective. Despite months of anticipation, despite the clear scientific value, despite every incentive to showcase their capabilities, silence. The European Space Agency represented yet another piece in this coordinated puzzle. Their Mars Express orbiter and ExoMars Trace Gas orbiter were both optimally positioned to observe 3I/Atlas during closest approach. ESA had publicly announced in September that observations would take place between October 1st and October 7th, providing specific dates and explaining which instruments would be employed. They specified that Mars Express would use its high-resolution stereo camera and various spectrometers to capture both images and chemical data. The Trace Gas Orbiter would employ its color and stereo surface imaging system along with its own impressive suite of analytical instruments. These weren't casual, opportunistic observations squeezed into spare moments. They were carefully planned, officially scheduled, internationally coordinated efforts involving multiple teams across numerous European nations, representing significant investment of time and resources. And then, silence as deafening as what came from NASA, China, and the UAE. The ESA public website showed no updates about 3I/Atlas observations beyond the original announcement. No press releases describing what was found. No preliminary findings shared with the global scientific community. No images added to their extensive Mars photograph archives. For an agency that routinely shares spectacular images from its various missions, that publishes results with admirable regularity, that takes pride in transparency and public engagement, This absence felt less like bureaucratic delay and more like deliberate information control. When observers began publicly noting this unprecedented coordinated silence across geopolitical lines that normally divide space agencies, some fascinating historical parallels surfaced in academic discussions. There have been moments throughout history when rival nations cooperated on matters of overriding mutual interest. The Partial Nuclear Test Ban Treaty of 1963, signed by the United States, Soviet Union, and United Kingdom at the absolute height of Cold War tensions, recognized that atmospheric nuclear testing threatened everyone regardless of political ideology. Radioactive fallout doesn't respect national borders. Space rescue agreements followed similar logic. The Apollo-Soyuz test project in 1975 saw American and Soviet spacecraft dock in orbit, crews shaking hands in zero gravity, while their nations remained in ideological opposition on Earth's surface. The common thread connecting these exceptional moments of cooperation: shared existential stakes. When something threatens everyone equally, or when something affects the entire human species rather than individual nations, rivalry becomes secondary to survival or collective understanding. The United Nations Office for Outer Space Affairs, established in 1998, has published guidelines, though not binding treaties, about how nations should handle the potential detection of extraterrestrial intelligence. These protocols weren't created casually. They emerged from serious academic conferences and governmental consultations about genuine possibilities. The recommendations emphasize that no single nation should make unilateral announcements about contact. Confirmation should be thoroughly verified through multiple independent observations. The international community should be systematically informed through proper channels. Premature disclosure could cause public panic, massive misinformation, or dangerous international incidents. And this represents a tremendously significant, if that cannot be overstated, the Mars orbiters observed something during the 3I/Atlas flyby that genuinely challenged the default assumption that it's a natural comet. You could construct a perfectly rational scenario where coordinated silence makes complete sense. Not as conspiracy or cover-up in the sinister sense, but as responsible protocol, as institutional caution, as a prudent attempt to verify findings before making public statements that cannot be retracted and would fundamentally alter human civilization's understanding of its place in the cosmos. But that scenario requires believing something genuinely extraordinary was observed, something that exceeded the threshold where normal scientific publication pathways seemed inadequate. And extraordinary claims, as Carl Sagan famously articulated, require extraordinary evidence. The silence alone isn't evidence of anything except that expected images haven't been publicly released. Mundane explanations certainly exist. Data processing genuinely takes time, especially for complex spectroscopic analysis. Quality control requires careful review by multiple specialists. Scientists understandably want to publish findings in peer-reviewed journals rather than through press releases, both to maintain professional credibility and to ensure priority of discovery gets properly documented. Yet the pattern remained deeply troubling to anyone paying close attention. 5 separate space agencies representing the United States, Europe, China, and the United Arab Emirates, all operating functional Mars missions with sophisticated instruments, all positioned to observe the same unprecedented event, all apparently choosing not to share results in the immediate aftermath of the closest flyby of an interstellar object in human history. 5 agencies that don't typically coordinate beyond unavoidable technical necessities, that actively compete for scientific achievements, prestige, and funding, suddenly perfectly aligned in their institutional silence. Online communities began tracking this obsessively with the dedication of investigative journalists. Reddit threads on r/space and r/astronomy accumulated hundreds, then thousands of comments analyzing every possible angle. Users noted with timestamps that Tianwen-1 routinely posted images within 48 to 72 hours of data acquisition for significant observations. They documented that ESA had shared Mars Express images just days after capture in previous instances involving scientifically interesting targets. They highlighted that the UAE's HOPE mission operated a public data portal specifically designed for transparency, updated regularly, suddenly gone dormant regarding this specific observation. Someone discovered that on October 1st, just 2 days before the Mars flyby, China's Tianwen-2 mission, an entirely separate spacecraft currently en route to collect samples from the asteroid Kamoolwa, released a spectacular selfie showing Earth in the background against the blackness of space. It was pure propaganda, beautifully composed, showing China's national flag prominently displayed on the spacecraft with our blue planet as dramatic backdrop. The timing struck observers as deeply significant. China was perfectly capable of processing and releasing space images during the exact time frame when 3I/Atlas observations should have been going through identical processing pipelines. They chose to release a Tianwen-2 selfie for propaganda purposes. They deliberately chose not to release Tianwen-1 observations of humanity's best-ever close-up of an interstellar visitor. Was this meaningful pattern or simply humans seeing conspiracy in coincidental timing, reading sinister intent into mundane bureaucratic delays? The silence spawned competing interpreters. Some saw a cylindrical craft with clearly defined edges. Others insisted it was mere compression artifacts and solar atmosphere effects. Professional astronomers who reviewed the image were skeptical. The enhancement processing was too aggressive, they argued. When you push contrast to extreme levels, noise becomes structure and random variations take on false significance. Our pattern recognition evolved to detect faces in clouds and shapes in shadows. It's kept our ancestors alive, helping them spot predators hiding in foliage. But it also makes us see meaningful patterns where none exist. The raw, unenhanced version of Dobsonian Power's image showed only a vague bright region, nothing clearly elongated. Whether the enhancement revealed hidden truth or created false structure remained hotly contested. What couldn't be contested was the mounting public interest. By mid-October, 3I Atlas had transcended astronomy communities and entered mainstream consciousness. News outlets ran features exploring whether an alien probe was passing through our solar system. Television programs invited scientists for debates. Podcast hosts dedicated episodes to analyzing the evidence. The story had everything a compelling narrative needs. Mystery, scientific disagreement, institutional silence, political implications, and the tantalizing possibility that humanity might not be alone in the universe. That we might be observed, studied, visited by intelligences from beyond our solar system. Public opinion polls conducted in mid-October showed fascinating splits. When asked whether 3I Atlas was a natural comet or artificial probe, roughly 60% of respondents selected comet, 25% chose probe, and 15% said they didn't know. But demographics mattered. Younger respondents were more likely to entertain artificial explanations. Those with science education split more heavily toward natural interpretations, while those without formal science backgrounds showed no strong preference. Education level correlated with skepticism about artificial origins, but not perfectly. Some highly educated scientists publicly stated the artificial hypothesis deserved consideration despite low prior probability. The generational divide was particularly stark. People who grew up with science fiction, with Star Trek and Star Wars shaping their imagination, seemed more psychologically prepared to accept that interstellar probes might exist. Older generations who remembered when space travel was pure fantasy, when rockets to the moon represented cutting-edge achievement, found the leap to artificial interstellar objects harder to make. Their intuitions about what was possible had been calibrated in different eras with different technological reference frames. There were cultural differences too. Some societies with long traditions of looking skeptically at official narratives were quicker to embrace conspiracy theories about government suppression. Others with stronger institutional trust were more willing to accept that data delays had mundane explanations. The internet allowed these different cultural approaches to clash in real time, creating information ecosystems where competing narratives strengthened within their own communities while becoming more polarized against opposing views. By October 20th, with perihelion just 9 days away, the online discourse had reached fever pitch. New websites appeared daily claiming insider knowledge. Anonymous sources allegedly from NASA or ESA leaked supposed documents, most obviously fabricated but some sophisticated enough to require expert analysis to debunk. Doctored images circulated showing 3i Atlas with structure that was never in the originals. Deepfake videos appeared featuring scientists saying things they never said. The information environment became polluted with false data, making it harder for genuine information to be recognized and trusted. In this chaos, a few voices tried to maintain rigor and evidence-based discussion. Science communicators published explanatory articles walking through the actual observations and what they could and couldn't tell us. Astronomers held virtual public lectures explaining cometary physics and why unusual chemistry doesn't necessarily imply technology. Skeptical analysts methodically addressed claims, pointing out where evidence was weak or misinterpreted. But measured voices struggled to compete with sensationalism. Algorithms favored engagement, and nothing engaged like controversy and extraordinary claims. The approach to perihelion also coincided with increasing unease about what the silence from space agencies truly meant. If the observations had shown nothing remarkable, why not simply release them and say so? A single press release confirming that 3i Atlas appeared as a normal comet in high-resolution images would have deflated much of the speculation. The continued absence of such a statement allowed theories to flourish in the vacuum. Every day without official images seemed to validate suspicion that something was being hidden. On October 25th, 4 days before perihelion, a development occurred that briefly dominated discussions. A researcher named Sarah Balliardo, working at the Planetary Science Institute, published a preprint paper analyzing the trajectory and arrival timing of 3i Atlas. Her calculations refined earlier work and added a new wrinkle. If you traced 3i Atlas backwards through space accounting for the gravitational influence of stars, it would have passed near over millions of years. The trajectory became increasingly uncertain. Small gravitational perturbations accumulate over time, making it impossible to precisely determine where the object was billions of years ago. But Balliardo focused on more recent history, the past few million years where calculations remained reliable. Her work suggested that 3i Atlas trajectory, when traced back approximately 7 million years, brought it within a few light years of a Sun-like star in the constellation Canis Major. The star, catalogued but not particularly famous, had a mass and spectral type remarkably similar to our Sun. It was old, several billion years, plenty of time for planets to have formed and for life to potentially have evolved. Balliardo calculated that if 3i Atlas had originated from a planetary system around that star and been ejected by gravitational interactions with a giant planet, the velocity and direction would approximately match what we observe today. This wasn't proof of anything. Tracing trajectories backwards through millions of years involves uncertainties. The star in question might not have any planets. Even if it did, we had no evidence they ejected anything. But the coincidence added one more thread to a tapestry already rich with improbabilities. Another Sun-like star, another statistical alignment, another piece that fit too neatly into a picture that might be real or might be pattern-seeking minds finding order in chaos. The paper generated immediate response. Some astronomers praised the careful orbital dynamics work. Others criticized assumptions about stellar positions millions of years ago, pointing out that stars move and that reconstructing ancient locations requires accounting for galactic rotation and local stellar motions, all of which introduce errors. Within 48 hours, 3 separate groups had published responses, 2 supporting Balliardo's conclusions with minor corrections, 1 arguing the uncertainties made any specific origin star impossible to identify confidently. The scientific process was working in real time. Publish an idea, let others scrutinize it, revise based on feedback, converge toward truth through collective effort. But the public mostly saw headlines. Alien comets home, star identified. 3I Atlas came from sun-like system. The nuance of uncertainty ranges and statistical confidence levels got lost in translation. People wanted definitive answers, and headlines provided them, even when the underlying papers offered only tentative suggestions. October 29th arrived not with fanfare but with quiet anticipation among those tracking the story closely. Perihelion would occur at exactly 1437 Universal Time Coordinated, the moment when 3I Atlas reached its minimum distance from the Sun, 1.36 astronomical units, approximately 203 million kilometers from the solar surface. At that instant, solar radiation would be at maximum intensity for this object. The temperature would peak. Outgassing would reach its zenith if thermal models held. And if something unexpected was going to happen, if the object was going to fragment or maneuver or reveal something about its nature, this was the moment. But from Earth, nothing could be observed. The geometry remained unfavorable. Ground-based telescopes pointed toward where calculations said 3I Atlas should be saw only the overwhelming glare of the Sun. Space telescopes in Earth orbit faced the same problem. The object was too close to the solar disk, lost in a region no optical instrument could safely observe without risking damage from scattered sunlight. SOHO registered something. The automated processing that converts LOSCO coronagraph images into viewable format showed a bright streak passing through the field of view on October 29th. The position matched predictions for where 3I Atlas should appear. The brightness was consistent with a moderately active comet at that distance. But resolution was insufficient to see structure, to distinguish between a point source and an extended coma, much less to detect any shape or features. SOHO confirmed the object existed and followed its predicted path. Beyond that, the data revealed little. Parker Solar Probe was farther from optimal position, but its wide-field imager captured background images that potentially included 3I Atlas in the far distance. Those images wouldn't be downlinked for days. Spacecraft have limited bandwidth. Transmitting gigabytes of image data across hundreds of millions of kilometers takes time even at radio speeds. Priority went to solar science data, the primary mission. The 3I Atlas observations would be transmitted when bandwidth allowed, processed when time permitted, published when analysis was complete. The timeline stretched into weeks. And so October 29th passed without revelation. Scientists who were watching knew what to look for in subsequent observations. If the object fragmented, pieces would separate over days, becoming distinguishable as multiple nuclei with their own comas. If a maneuver occurred, the trajectory would deviate from gravitational predictions, becoming measurable once enough post-perihelion position observations accumulated. If the chemistry changed dramatically, spectrographic observations in November and December would show different emission lines, altered ratios of volatiles, evidence that perihelion had transformed the surface composition. In early November, the first post-perihelion data began trickling in, not from spacecraft but from a solar observatory in Chile that had been monitoring the region just beyond the sun's glare. The images were marginal, captured at extreme solar elongation angles where atmospheric scatter made observation difficult. But they showed 3I Atlas still intact, a single bright coma with no obvious fragmentation. The nucleus had survived perihelion. That survival told scientists something important. The object wasn't a loosely bound rubble pile that would disintegrate under thermal stress. It had structural integrity, either from being a coherent solid body or from having strength beyond what random aggregation provides. Natural comets can certainly survive perihelion intact, many do, but combined with everything else, the survival added one more data point suggesting substantial structural cohesion. On November 2nd, ESA announced that the JUICE spacecraft had begun its observation campaign. Initial images were being received and would be processed over the coming days. The announcement was brief, offering no preliminary findings, no description of what the images showed, just confirmation that observations had occurred successfully. The measured tone was typical of scientific institutions that prefer to analyze data thoroughly before making public statements. But after weeks of silence, even this brief announcement felt significant, like the first crack in a dam holding back information. JUICE images, when they were finally released on November 9th, showed a comet. A bright central condensation surrounded by an extensive coma stretching into a tail that extended millions of kilometers away from the sun. The tail showed structure, streamers and filaments visible in high-contrast processing, evidence of complex interactions between solar wind and the outgassing material. The colors indicated strong carbon monoxide and carbon dioxide emission with hints of cyanogen. The green glow that had been visible in September observations had faded somewhat but remained detectable. What the JUICE images didn't show was clear structure in the nucleus. The resolution wasn't sufficient to resolve features at the nucleus level. It remained a bright point source or small disk even in the best images. The size could be estimated from brightness assuming a reasonable albedo. Estimates placed it somewhere between 3 and 10 kilometers depending on assumptions about reflectivity and composition. That range included everything from a modest comet to a large one, but nothing like the 20 kilometers that early estimates had suggested. Either those early size calculations had been wrong, based on overestimating albedo, or most of the brightness came from an extended coma rather than a solid nucleus. The elongation debate remained unresolved. JUICE images showed a somewhat non-circular brightness distribution, but atmospheric effects and the viewing geometry made it impossible to determine if that represented true structural elongation or simply how the coma was being viewed from that particular angle. Different observers analyzing the same images reached different conclusions, seeing what their prior expectations led them to see. The ambiguity persisted. By mid-November, enough observations had accumulated that trajectory specialists could calculate whether 3I Atlas had experienced any measurable change in velocity or direction beyond what gravity and normal cometary outgassing would predict. The analysis was complicated. Comets experience rocket effects when gas vents preferentially from one side, creating thrust that alters trajectories. Calculating these non-gravitational forces requires modeling the rotation rate, the location of active vents, the amount of outgassing, all parameters that aren't directly observable. You're fitting models to limited data points, and multiple models can fit equally well. The preliminary conclusion from several independent groups was that 3I Atlas showed non-gravitational acceleration consistent with typical cometary outgassing. The trajectory had changed slightly, but not in ways that required invoking deliberate maneuvering. The object appeared to be following physics familiar from decades of studying solar system comets. It was responding to solar heating by releasing gas asymmetrically, and that gas was pushing it in measurable ways. All perfectly normal for an active comet near perihelion. But the uncertainty ranges on those calculations were large enough that they couldn't completely rule out small deliberate maneuvers hidden within the noise. If 3I Atlas had changed velocity by a few meters per second through propulsion rather than outgassing, that would be difficult to distinguish from natural effects given current measurement precision. Only over months as the trajectory continued to be refined would unusual deviations become statistically certain. For now, the trajectory looked natural with asterisks noting that subtle anomalies couldn't be excluded. By late November, the chemical analysis from multiple observatories showed something interesting. The nickel emission had dropped dramatically after perihelion. The production rate that had been increasing steeply according to that power-law relationship peaked somewhere around perihelion and then fell off sharply. By mid-November, nickel emission was barely detectable, far weaker than the pre-perihelion observations had suggested it would be based on distance-based models. What did this mean? One interpretation was that the surface reservoir of nickel-bearing materials had been depleted. Whatever was producing nickel, whether exotic minerals or carbonyl compounds or something else, had been exhausted by the intense outgassing at perihelion. The surface had been stripped of its volatile nickel sources, leaving deeper materials that didn't release metals as readily. This would be consistent with a layered composition where the outer surface was chemically distinct from the interior. Another interpretation, more provocative, was that the nickel release hadn't been passive sublimation but active venting from specific locations that had now been sealed or deactivated. If vents had been releasing metal-bearing gas under pressure driven by internal heating or by some other mechanism, and those vents closed after perihelion, the emission would drop sharply. Natural processes could explain this. Vents seal themselves when outgassing blows away material that then redeposits in the vent opening, or when pressure drops below the threshold needed to keep the vent open. But the sharpness of the decline, the fact that it didn't taper gradually but rather dropped precipitously, made some observers wonder if something had been turned off rather than something passively declining. The cyanogen emission behaved differently. It remained elevated into late November, decreasing more slowly following thermal expectations. Whatever was producing CN continued to operate as the comet moved outward from the Sun, with activity declining in proportion to solar heating. The difference between nickel's sharp drop and cyanogen's gradual decline suggested they were coming from different sources or through different mechanisms. Natural chemistry could account for this if nickel and cyanogen came from different depths or different surface features. But it added another layer of peculiarity to an object that seemed to specialize in peculiarities. December arrived, and finally 3I Atlas emerged from solar conjunction, visible again from Earth. Amateur astronomers across the planet rushed to observe it, posting images to forums within hours of successful captures. The comet had changed. The tail was now spectacular, extending several degrees across the sky in long exposure photographs. The green coma remained visible, though fainter than in September. The overall brightness had increased, then begun declining as the comet moved farther from the Sun on its outbound path. The shape debate flared again immediately. Some of the early December images from observers with excellent equipment and atmospheric conditions showed what appeared to be an elongated central condensation. Not dramatically elongated, perhaps 2-to-1 ratio, visible when processing was pushed to enhance faint features. Other observers capturing the same comet at the same time saw circular condensation with no elongation. The disagreement wasn't about dishonesty. Both camps were looking at real data. It was about interpretation, about how much weight to give marginal features that appeared at the threshold of detectability. One observer in Australia using a 14-inch telescope and a highly sensitive CCD camera captured an image that generated immediate intense discussion. In his carefully processed image, the central region showed a distinctly non-circular shape with what appeared to be straight edges. Not curved like a natural object would be, but angular, geometric. He posted the image with careful notes about his processing steps, the exposure time, the atmospheric conditions. Within hours, other observers were attempting to replicate his results, pointing their telescopes at 3I Atlas and processing their images using similar techniques. Some succeeded in seeing similar features. Others captured images showing no such structure. The split wasn't random. Observers using certain types of cameras and certain processing algorithms tended to see the geometric features. Those using different equipment and techniques didn't. This pattern suggested the features might be artifacts of the specific imaging and processing chain rather than real structure on the object. But it was also possible that only certain equipment combinations had sufficient sensitivity and resolution to detect subtle features that other setups missed. Professional astronomers observing with major telescopes published preliminary results in mid-December. The Keck Observatory in Hawaii, the Very Large Telescope in Chile, and the Subaru Telescope in Japan all captured high-resolution images and spectra of 3I Atlas. Their results were careful and measured. The object appeared consistent with a comet. The spectrum showed emission lines from standard cometary molecules. The morphology revealed a coma and tail with structures similar to other comets. The nucleus size estimates ranged from 3 to 6 kilometers, nothing exceptional. Critically, none of the professional observations showed clear evidence of elongation or geometric structure. At the resolution limits of even the best telescopes across interplanetary distances, the nucleus remained unresolved, a point source or small disk without distinguishable features. You would need spacecraft proximity observations or much larger telescopes to definitively resolve surface features or confirm unusual shapes. Without that capability, the shape question remained formally unresolved, though professional astronomers largely concluded elongation was likely an artifact of the various imaging factors that had been discussed for months. The media coverage began to wind down in mid-December. 3I Atlas continued to be observed by dedicated astronomers, but the general public's attention shifted to other matters. The story had played out without definitive resolution, and stories without clear endings struggle to maintain interest. Some outlets published retrospectives. What had we learned from 3I Atlas? What did the controversy teach us about scientific communication in the social media age? How should space agencies handle potentially sensitive observations in the future? Scientific papers began appearing in journals, having passed through peer review. Studies on the trajectory, the chemistry, the observed morphology, each adding pieces to the comprehensive understanding. The conclusions across papers were generally consistent. 3I Atlas was an unusual interstellar comet with several anomalous properties that pushed the boundaries of normal cometary behavior but didn't definitively exceed them. The chemistry was bizarre. The nickel emission was unprecedented. The carbon dioxide dominance was extreme. But all of it could be explained, however awkwardly, through natural processes given sufficient special pleading about formation conditions and compositional peculiarities. The artificial hypothesis wasn't validated but also wasn't definitively refuted. Absence of evidence isn't evidence of absence. The fact that no clear technological signatures were detected doesn't prove they weren't there. Only that our observations weren't sufficient to detect them if they existed. Some papers included sections explicitly addressing the question, calculating what kinds of technological features would have been detectable given the resolution and spectral coverage of the observations. The conclusion: anything subtle would have been missed. Only blatant artificial structure, obvious geometric patterns, clear waste heat signatures, or similar strong indicators would have been detectable. The absence of such signatures meant either the object was natural or any artificial elements were designed to avoid detection. Avi Loeb published a comprehensive paper in late December summarizing all observations and discussing both natural and artificial interpretations. His conclusion was carefully worded. The natural explanation remained more probable based on Occam's razor and the principle that extraordinary claims require extraordinary evidence. But the artificial explanation couldn't be dismissed entirely. The number of anomalies, while individually explainable, collectively strained credulity. He advocated for continued observation as 3I Atlas moved outward, for attempting radio communication though response times would be long, and for designing better instrumentation specifically to detect and characterize interstellar objects in the future. His paper also addressed the social and policy dimensions. If interstellar objects are relatively common, and if there's even a small probability that some fraction are artificial probes, then humanity needs detection networks capable of identifying them early. The object that eventually provides definitive evidence of extraterrestrial technology might be detected when it's still far from the sun, approaching from deep space. Early detection would provide time for comprehensive observation, for coordination, for preparation. Missing such an object because our sky surveys aren't sensitive enough or because we assume every asteroid-like detection is natural would be a failure of imagination and preparedness. By late December 2025, 3I Atlas was beyond Mars' orbit on its outward journey. It would continue to be observable from Earth for several more months as it gradually faded, moving back into the realm of objects requiring serious telescopes rather than backyard equipment. Eventually, it would fade below detection thresholds, disappearing into the vastness of space, leaving the solar system on its hyperbolic trajectory, bound for interstellar space once again. In perhaps 100,000 years, it might enter another stellar system, passing another star with its own potential planets and civilizations, carrying whatever secrets it holds. The controversy it sparked would be remembered as a case study in how science handles anomalies and how society processes potentially paradigm-shifting information. The episode revealed strengths and weaknesses in our systems for investigating anomalous phenomena. The strengths included the rapid mobilization of observational resources, the international cooperation in sharing data despite geopolitical tensions, and the rigorous application of scientific skepticism that prevented premature conclusions. The weaknesses included the initial coordinated silence that bred conspiracy theories, the difficulty in communicating uncertainty to a public wanting definitive answers, and the chaotic information environment where false claims mixed freely with legitimate analysis. What remains is a collection of data points, some confirmed, some uncertain, all pointing toward an object that was remarkable even if entirely natural. 3I Atlas reminded humanity that the universe is vast, that our sampling of cosmic phenomena is laughably incomplete, and that interstellar space likely harbors wonders we haven't imagined. Whether 3I Atlas was one of those wonders or merely a strange rock, it served a valuable purpose. It forced us to look upward with fresh eyes, to question our assumptions, to grapple with possibilities that challenge comfortable paradigms. The core question, what was 3I Atlas, received no definitive answer, at least not in 2025. Maybe future observations will provide clarity as astronomical capabilities improve. Maybe another interstellar object displaying similar properties will arrive providing comparative data. Maybe decades hence, archive data will be reprocessed with better algorithms revealing details we missed. Or maybe the mystery will persist, 3I Atlas joining the list of cosmic curiosities where evidence tantalizingly suggests something extraordinary without quite proving it. For now, we return to our daily lives under the same sky our ancestors watched with wonder. The stars remain ancient and distant, their light carrying stories we're only beginning to learn to read. Somewhere among those stars, perhaps civilizations look outward as we do, sending their own probes, asking their own questions, wondering if they're alone. And perhaps one of their probes passed through our solar system, observed us, and continued onward, carrying knowledge of our existence back into the darkness between stars. Or perhaps 3I Atlas was simply a comet, ancient and strange, forged in conditions we don't understand, following a random path that happened by chance to bring it through our neighborhood. Either answer is profound. Either answer reminds us that reality is richer and more mysterious than our theories encompass. The images from Mars that ignited this investigation hang in digital archives now, pixels preserving a moment when humanity looked at something in the sky and couldn't immediately explain what it was seeing. Future generations might look back on October 2025 as the moment when we first seriously grappled with evidence of extraterrestrial technology, the beginning of a new chapter in human history. Or they might see it as an interesting footnote, a case where unusual chemistry and imaging artifacts combine to create false patterns, teaching us valuable lessons about the care required in scientific interpretation. Both futures are possible. The truth, whatever it is, exists independently of our ability to determine it. 3I Atlas knows what it is, even if we don't. The atoms that comprise it, whether arranged by stellar nucleosynthesis and random cosmic processes or assembled deliberately by intelligent beings, carry their history encoded in isotopic ratios, in crystal structures, in the precise arrangement of molecules. If we could somehow retrieve a sample, subject it to laboratory analysis with instruments far more sophisticated than telescopes can provide, the answer would be clear. But that capability lies decades in our future if we achieve it at all. So we're left with inference, with probability assessments, with models and calculations that approximate truth without touching it directly. We're left with wonder, that most human of emotions, the feeling that arises when we encounter something larger than our current understanding. And perhaps that's appropriate. Perhaps wonder is the right response to the universe's vast mysteries. Not certainty, not dismissal, but engaged curiosity combined with epistemic humility. The willingness to say, I don't know, while continuing to investigate, to gather evidence, to refine our understanding incrementally toward whatever truth awaits discovery. Thank you for taking this journey through the evidence, the debates, and the implications of 3I Atlas. The story of this interstellar visitor represents more than astronomy. It touches on philosophy, on the nature of knowledge, on how we decide what to believe when evidence points in multiple directions. It challenges our assumptions about what's normal and what's extraordinary, about where we draw lines between natural and artificial, random and designed. If you've made it to this conclusion, you're part of a community that values deep exploration over superficial headlines. Show your support by leaving a comment below telling me, what do you think 3I Atlas truly was? Natural comet or something more? Your perspective matters, and I read every thoughtful comment. Hit that like button to signal that content like this, detailed investigations that respect your intelligence and don't shy away from complexity, deserves a place in your feed. Subscribe and enable notifications so you don't miss future deep dives into the mysteries at the edge of our knowledge. The universe is speaking to us in languages we're only beginning to understand. Photons carrying information across billions of kilometers. Gravitational waves rippling through spacetime from colliding black holes. Neutrinos streaming through our bodies from fusion reactions in the sun's core. And occasionally, physical objects wandering between stars, ambassadors from distant systems bearing clues about processes and perhaps civilizations we've never encountered. Our challenge is learning to read these messages, to extract meaning from sparse data, to distinguish signals from noise in observations at the absolute limits of our technological capabilities. 3I Atlas offered such a message, whether in the form of chemical signatures from an alien star system's planetary formation, or possibly something more. We listened, we observed, we debated, and we learned, even if our learning didn't provide the definitive answers we craved. That's how knowledge grows, incrementally, through accumulation of observations and careful reasoning, through the willingness to follow evidence wherever it leads even when destinations are uncomfortable. The next interstellar visitor is already en route, somewhere in the vast gulf between stars, following its trajectory toward our solar system. It might arrive next year or 1,000 years hence, but it will come. And when it does, we'll be better prepared than we were for Oumuamua or for 3I Atlas. Our telescopes will be more sensitive. Our coordination will be better practiced. Our frameworks for evaluating artificial versus natural origins will be refined by the debates this object sparked. Until then, keep watching the skies. Look upward on clear nights and remember that some of those points of light are not stars but wanderers, objects moving through the cosmic ocean on journeys that dwarf human timescales. And perhaps among those wanderers, something watches back, recording our electromagnetic signals, analyzing our atmospheric composition, documenting the emergence of technological civilization on this small blue world orbiting an unremarkable yellow star in the outer regions of the Milky Way galaxy. Whether 3I Atlas was one such watcher or simply a cold rock adrift in eternity, it reminded us that we live in a universe far stranger and more wondrous than our daily routines allow us to remember. It reminded us to question, to investigate, to remain open to possibilities that challenge our comfortable assumptions about reality. And it reminded us that the greatest discoveries might come not from deliberately seeking them, but from paying attention when something unexpected crosses our path. Rest well, stay curious, and never stop wondering what else might be out there waiting to be discovered. The cosmos is vast, ancient, and full of secrets. Some of those secrets might be technological rather than geological, intelligent rather than random, messages rather than noise. Our responsibility is to be ready to recognize them when they arrive. Good night, and remember, the truth is out there, we just need better telescopes and more courage to find it.